Good afternoon. Welcome back to ECE 320A. It's time to sort of quiet down. Few announcements. The passport, you should be aware that it's due on Sunday. You need to be starting to read chapter 10 so that you can do homework number 1, which isn't due for a while, but I've made it due on a Sunday evening. We'll try that and see how that works. And I'm just telling you now when the first exam is, and that's the 24th of September. That's a Thursday, just so that you're continuing to think about when am I responsible. And I believe we will have 2 homework assignments prior to that date, and the assignment 1 and I believe 2 are available on mastering. You probably don't want to attempt homework 2 just yet, but homework 1, I think you'll start to be able to work some of those problems after today's class. That's the idea. Today what we want to do is begin chapter 10 material, which is single phase, and I may write that out or I may just say 1-phi for single phase. That's in contrast to chapter 11 where we will have 3 phases, so it will be 3-phi. But now we're just learning the fundamentals or the basics, and that's single phase power. We'll work through a generic single element. How can we identify the power associated with that single generic element? We can have instantaneous power. Here are some formulas that you probably need to get comfortable with. There's the average power that we talked about last time, and you can see that there are no scaling coefficients in there. There's no 1/2 in there because though the 1/2 has been absorbed in as the square root of 2 times the square root of 2 underneath the Vmax and the Imax, and those have been absorbed into a magnitude value for VRMS and a magnitude value for IRMS. And those are scaled or adjusted by the cosine of the angular difference between the voltage of that element and its current through that element. That's the average power formula, where V and I in that formula are just numbers. Contrasting that with the last equation on the screen right now, which is complex power, I may be consistent, I may not, but that one now has bars over it. That means those are phasors. That in the bottom with complex power says that complex power is a complex number, which could be written in rectangular form or polar form. But you can find that if you know the voltage of an element and its current, then you can multiply the phasor voltage times I star. And that's not convolution in this case. That's the complex conjugate. And that wouldn't make sense if these were unbarred, to have a conjugate symbol above a number. You can't conjugate a number, you need a complex value to conjugate it. We will work through these particular concepts for specific elements being resistors, inductors, and capacitors. And we'll see what they look like relative to average power, and we'll have to introduce another power, which is reactive power. And the combination, and it's a particular combination of real power and complex power creates, average power or real power and reactive power. That orthogonal combination goes into creating the complex power. And we'll see that as we work through this material. Here's chapter 10. I wanted to write this down so that if you don't understand what I'm trying to say, you can go back and read it. And these notes should be available on D2L. I'm assuming you haven't had any trouble accessing D2L if you've tried. And you should try to make sure that you can gain access to the Mastering Engineering site. Now you do have homework that you can start looking at, maybe not completely solving, but you can at least start that process. Here is a generic element, and you could view that element to mean a collection of elements, actually. But we will be using the passive sign convention. And what that means is that we will have the product of V and I with a positive sign out in front when the current, as you have defined it, whichever direction you've defined it. Here I've directed the current to go from left to right. It's positive as far as I know, but if it turns out to be negative, the signs will take care of themselves. But now I'm saying the current that I am going to be using, I'm directing from left to right, and it's actually entering the positive terminal as I've defined it for that generic element. It's entering the positive terminal before the current actually flows through the element. That's the passive sign convention, and we assign a positive value to that product of V and I when they are oriented in that direction. And that's the amount of power absorbed by that generic element. I want that to be clear, and that's what we will be using, which means if it ended up that the power absorbed was negative, then really you could think of that power being supplied to the rest of the circuit. Is that clear? But we will just say, oh, the power absorbed will be positive if the current that we've labeled is going into the positive terminal of that device or that element. Let's now establish some notation. And if you've read the bad study habits or the good study habits, I'm really sort of assuming you're playing along as I'm doing this. You're actually physically writing things down, trying to make that. It helps actually as you mechanically write to connect what you're thinking with your brain. So let's now get started and say that suppose that for notation reasons, V of t that we just defined above, let's call that V sub m, capital V sub m, cosine omega t plus theta sub v. Or we know the relationship for sinusoids between RMS and maximums, so that we could say that this is square root of 2 V RMS cosine omega t plus theta sub v. And let's just say that I of t is now I sub m cosine omega t plus theta sub I, and that likewise can be referred to as the square root of 2 I RMS cosine omega t plus theta sub I. It will actually be easier if these now waveforms are sinusoidal, and we've converted or we've started those out to both be cosines. If one was a sine, we could change it into a cosine, and now we can start playing with those. You don't want to have an angle of a voltage and an angle of a current and subtracting those yet. If you have a sine and a cosine, you don't want to mix sine and cosine and angles. You want to convert them both to cosines and then start comparing angles or subtracting or dealing with the angles. We now have these two cosines. They're at the same frequency, omega. They are just shifted in time relative to each other because of this phase shift. And you're all aware that a lot of times we get sloppy with how we refer to omega t and theta. They may not have the same units. We like to think in angles of degrees, and a lot of times we will have theta sub v or theta sub I as 30 degrees and 50 degrees, for example. Yet omega is in radians per second, and t is in seconds, so now inside that argument we have radians plus degrees. take the cosine of that without getting a mistake, meaning you need to convert one to the other depending on what mode your calculator is in. If you're dealing with radians, then convert the angles to radians before you combine those two pieces. Is that clear? But a lot of times it's convenient to keep theta sub v and theta sub I as degrees and omega in radians per second. Now that these waveforms are just bouncing around, I'm going to draw a line in the sand or on the whiteboard and say, here is time 0, t equals 0. And I'm going to let the current peak at time 0. But I still want to keep track of the difference between the voltage angle and the current's angle. So I'm going to basically take the difference of theta sub v with theta sub I and put that in my cosine so that I can now make the peak at time t equals 0. So I'm really not doing too much other than establishing a time reference to make maybe the discussion or the analysis a little cleaner. The time reference now is I'm going to select my time in the sand, or when I say here is 0, select t equals 0 to be when the current peaks. That allows me now to rewrite these. I can say that v of t is now v sub m cosine omega t plus theta sub v minus theta sub I, and I of t is I sub m cosine omega t. And now the current is going to peak at time t equals 0. But I still want to keep track of the time difference or the phase shift between the voltage and the current, so I'm not going to forget the angle of my current. I'm going to put it up into the voltage expression. And I hope that you're comfortable moving back and forth between maximum or peak values and RMS values. Here I'm using the maximum values again. But let's now look at the instantaneous power. This is the easy one in terms of the formula. We just multiply voltage and current at each instant of time, and that's the power at that particular time. We now have that's equal to v sub m I sub m cosine omega t plus theta sub v minus theta sub I. Now, I've run out of room on my paper. I can cheat. I could actually just keep going and going, but that's frustrating for you maybe because your page is only 8.5 inches wide. So I won't do that. I will sort of do this and say that I'm supposed to be multiplying that times the cosine piece associated with the current. Is that clear what I'm doing? I'm just multiplying those two together. Does everyone remember their trig identities? Shouldn't be laughing. That's not funny. Should be having these sines and cosines and just floating around all the time. What do I have? I actually have two cosines that are multiplied together. Suppose that I call this argument alpha, and let me call this argument beta. And we'll just step aside for just a minute and remind ourselves and that I think that we want is in Appendix F of your textbook. where now we have cosine of alpha, cosine of beta. That's what we have up above, and we want to convert that into a sum of two terms. And if you don't remember, that's 1/2 cosine alpha minus beta plus 1/2 cosine alpha plus beta. And tonight, if you wanted to prove that or verify that to yourself, sit back, put your feet up, and apply Euler, right? Just think Euler and say, do you remember Euler's formula? Cosine of x, e to the jx plus e to the minus jx over 2. You can use that with alpha and beta and verify that indeed, oh, I just have to do some multiplication and I've now proved a trig identity. I'm not going to do that now. I will let you enjoy that this evening. Again, is that really that funny? You're an engineer, right? This is, never mind. All right. So now we have P of t, and we can apply that formula. We now have a 1/2 out front, and we just take the difference of alpha and beta in the argument of cosine for our first term. We now have 1/2 Vm cosine, and, well, let me just, if we take alpha and subtract beta, do you see that theta sub v minus theta sub I is all that's left in the argument of those two? That's where this is coming from. Then we have plus the second term, 1/2 Vm Im cosine of 2 omega t. Now we're adding those two arguments. And that's now the instantaneous power of that generic element that had a voltage as a cosine and a current as a cosine. And the power company probably doesn't track that every second of every day. I mean, they have to produce that and supply that and deliver that, but they're probably not going to want to show you in your bill what your power looked like instantaneously. You probably don't want to know that either, right? Maybe hour by hour you want to know your energy consumption, but we can, if you wanted to, you could, well, let's go ahead and do that. Suppose we introduce some more formulas to try to get this into another structure that we are comfortable with. And now let's look at a trig identity number 2, where we have cosine alpha 1 plus beta 1, and this now becomes cosine alpha 1 cosine beta 1 minus sine alpha 1 sine beta 1. And that now allows us to break that second term in the black formula into two parts. The first part remains the same. That's v sub m I sub m over 2 cosine theta sub v minus theta sub I. But now we have plus 1/2 Vm Im cosine 2 omega t. Well, let me reverse that just because it'll be a little bit cleaner. Let me call this the theta sub v minus theta sub I cosine 2 omega t. And then I have a minus 1/2 Vm sine theta sub v minus theta sub I sine 2 omega t. What we are going to pay attention to are the constants in that expression. Can you now identify some terms in there in that three-term expansion that are constants? And I'll identify v sub m and I sub m. Are there any other constants in that expression? The 1/2, okay, I should have taken that myself. That one I'll take too. So now omega is fixed. That's maybe 377 coming out of the wall. But t is our independent variable, isn't it? This term, well, maybe I should. This term and that term are not constant, are they? Cosine of 2 omega t, that's a function of time. Sine of 2 omega t is a function of time. Everything else is actually a constant. This the angle of the voltage is a fixed angle. The angle of the current is a fixed angle for that particular element. Now we just have cosine of some angle. And cosine of 20 degrees is just a number. We now have Vm over 2 times that number. Likewise for the next two terms. This is also a constant, as is the sine of that angle. And what we're interested in, I said we may not want to be tracking this all the time. Maybe we want to try to collapse this down a little bit. What if we look at the average of the instantaneous power? This is actually the real power, or the average power, and I'll refer to it many different ways, but now I will say that's capital P, and I'll subscript it with average now to make that clear. How would we average that P of T expression? We could have gone back to the beginning of time and gone ahead to now and averaged over that entire time interval and divided by that time. That's probably more than we want to do, isn't it? But we do know something about when this starts repeating as a function. What's omega? That's the frequency. And if I give you a frequency, can you find the period associated with that? Yes. So now you know the period of these waveforms. If I wanted the average value of this little p of t, I could just average over one cycle or over one period, and I would be good, because it looks exactly the same from period to period. Meaning, now my p average is 1 over t. That's the period. Let me just say from 0 to t of little p of t dt. Where t is related to omega, this is something you probably want to remember until you retire also. And maybe you'll hit it big and you can retire in 4 years. Maybe you can retire in 5, so you don't have to remember it that long. But omega is 2 pi f, or 2 pi over cap t. We know t. If I now integrate these three terms over that time interval, what's going to happen to those terms? Can you already predict what's going to happen to some of those terms? The cosine is what? It has the same amount of positive hump as it does negative hump, and if we integrate over that in one interval, then it would integrate to 0, wouldn't it? And we actually have twice that, so it's 2 cycles in that one period, capital T. And if we have an even number of periods to integrate over, that's going to integrate to 0. Taking the average of this little p of t, I hope it's clear that these last 2 terms integrate to 0, because the only thing in front is just a number of both of those, and that comes out of your integral. And now you're integrating a cosine or a sine over an integer number of periods, which in this case is 2. What I'm trying to say is that the cosine of 2 omega t and the sine of 2 omega t, those 2 terms integrate to 0. And now what's the integral, or what's the average, I should say, of that first term? What is that first term? If I said integrate 5 over a half of a second, let's say that was my period, what's the average of 5? 5, right? I just have the integral of 5 with respect to t. I'll get 5t, and I'm integrating from 0 to whatever t was, big T. So now I just have that very first term after the integration, so that now P average is simply that constant 1/2 Vm Im cosine theta sub V minus theta sub I. And we may want to write that in terms of the RMS units, where we distribute that 2, we cut it in half, basically. We have the square root of 2 times the square root of 2, and we put one of those square roots under V and one under I, so that now we have VRMS IRMS cosine theta sub V minus theta sub I. Those are equivalent formulas. It's just one of those is written in terms of maximum values on our cosines, and one is in RMS units. The bottom one is probably the one that I would keep track of. This is the average power, or the real power, associated with this generic device that had the voltage and current as we defined them. The average power then, or the real power, this is actually what you use day in and day out, is real power. This is what measures the rate of energy consumption let's say used to transform from electrical energy to another energy, where that other energy may be non-electrical. Maybe you're using that energy to drive a motor. Maybe you're using it to charge your cell phone or your computer. that is now the real power that's being used. And what does your home, on average, consume? 1,000 watt, or it's demanding 1,000 watts, 24/7. That's just an average number. If somebody said, oh, what's the power usage of these 30 homes in this development, you could say 30 kilowatts. And they would go, that was pretty close. You have the job, right? All right, so now let's look at some specific impedance elements. We have resistors, inductors, and capacitors. Let's look at all three of those and see how they are impacted by these formulas. Because that was derived for a generic element. What's the impedance of a resistor in sinusoidal steady state? That's what we're playing with now. We're assuming we are in sinusoidal steady state. All the transients have died out. What are we going to use for the impedance of a resistor? Just R. What do we know if we have a real impedance? What do we know about the relationship between the angle of the current and the angle of the voltage, or the current and voltage phases? They're the same, aren't they? They're in phase. Or, using our terminology from earlier, theta sub v is equal to theta sub I, if they have the same phase. Now those cosines are moving together. There's no time shift between them if you just had a pure resistive load. If that's the case, what is our average power of a resistor? Cosine of 0, we have to remember that, and that's 1. So the average power of a pure resistor is just the product of the voltage magnitude in RMS and the current magnitude in RMS. And that one looks very familiar to us. And those are two numbers. Those aren't phasors. If they were phasors, you would just pull the magnitude of each. Well, in this case, you could sort of view them as phasors, but the angles are the same, so you don't have to worry about their angles. And now you just have this. And what are the units? Watts for real power. Now we need to step it up a little bit and look at inductors and capacitors. And do you remember Eli the Iceman? Yes? Eli the Iceman, that's something else you probably want to try to keep in your head, at least for this semester or beyond. But this now gives you a way to remind yourself of the current voltage relationships of inductors and capacitors. Meaning, this Eli, you could say, oh, the voltage of my inductor, V sub L of t, is equal to L di sub L dt. And the current of my capacitor is C dV sub C dt. But really why right now we're interested in Eli the Iceman is to understand the relationship between the phases of voltage and current in those two reactive elements. And Eli the Iceman actually gives us a visual way to keep track of that. If you looked at Eli as a combination of three letters, and now we're comparing voltage, which is E, and current, which is I, how are they related? Which one comes after the other? I feel like I'm in Sesame Street. One of these letters, so the voltage is in front of the current, so the voltage is leading, or the current comes after the voltage. The current lags the voltage. That's the term that we will probably more commonly use, is lagging. The current lags the voltage in an inductor. Let me write that down. The current in Eli, in that expression, comes after the voltage, which we will probably just say, oh, the current lags the voltage in an inductor. And if you forget leading or lagging on an inductor, Eli. Just use Eli and say which one is where. Oh, the voltage is ahead of, so the current is lagging the voltage. What about ice? Now the current and voltage have switched places, haven't they, effectively? And now the current comes before the voltage. And we say then that the current leads the voltage in a capacitor. So just with Eli and ice, we now know this current voltage relationship between the inductor and the capacitor, which one's lagging, which one's leading. And you're going to be playing with that a lot as we deal with power. Now look at the second impedance element, which is this inductor, Z sub L. What's the sinusoidal steady state formula for an inductor's impedance? J omega L. And sometimes we will simply combine the frequency omega with the inductor's value L and call that the reactance X sub L. Now, what is P average for an inductor? What's the real power of this inductor? Well, now we can go back and we can say, well, in an inductor, in a pure inductor, no resistance is present. We know that the current lags the voltage. That's from Eli. And we know Ohm's law. And the voltage and the current can both be phasors. The impedance Z, I'm not going to indicate that, but that's a complex number. And if V and I are both phasors, let's say that we now have V RMS at some angle theta sub V, and now we have Z sub L, which is J omega L. This is now I RMS angle of theta sub I. What's another way of writing this complex number? That's now sort of in rectangular form, isn't it? It's 0 plus J some value, omega L. That's a complex number in that parenthetical representation. And it's in rectangular form. How do I convert that to polar form? Since all my others are effectively in polar form, they're in phasor form. How do I write J X sub L in polar form? Now, if you forget this, here's your complex plane, real and imaginary. Everything that's real is horizontal. Everything that's J is vertical. What do I have here? I just have vertical, don't I? Ceiling's tall enough. If I wanted to write J on this, wouldn't it be right there? I would go up 1 in the J direction. There is J. If I now want to write that in terms of magnitude and angle, and I'm measuring all of my angles relative to this horizontal real line going off in the positive direction, what's that angle? 90 degrees. So this now you could write as omega L at 90 degrees. Is that clear? We've now converted that rectangular complex number into its polar form. It has a magnitude of omega L at an angle of 90 degrees. We know about the phase now relationship of theta sub v and theta sub I. If we just looked at the angular part of that expression, we have sum and difference going on when we're computing with angles. We can now say that in terms of the phase relationship in that formula, we know that the voltage phase on the left must be equal to what phase is on the right. And how do we combine those angles in phasor form? This you could think of as V RMS e to the j theta sub v. This is now omega L e to the j 90, and this is I RMS e to the j theta sub I. How do we combine those phases or angles? They just add, don't they? Now theta sub v is going to be 90 degrees plus theta sub I. Or our formula for average power was dealing with the difference between our voltage angle and the current angle. If we subtract theta sub I from both sides, we end up with the expression that we need, theta sub v minus theta sub I, and that's equal to 90 degrees. We can now go back to our initial question and say, what is P average for an inductor? It's V RMS, I RMS cosine of theta sub v minus theta sub I, but we now know that's 90 degrees. What's the real power of an inductor? 0. This is an energy storage element. It's not absorbing any real power. It's just the magnetic field is storing energy, and then it just releases it. It stores it, releases it, stores it, releases it. 3 more. Stores it. Sorry. So we have 0 real power or average power of an inductor. But now, are you going to be able to argue that very persuasively with the power company? They're going to say, what do you mean I shouldn't be billing you? I don't have any real power. Yes, but you're drawing current from my power facilities. So where is that current going? Well, if we go back to that early derived instantaneous power formula, what can we see from that? The first term vanishes, doesn't it? What about the second term or the middle term? It's gone also. What about the third term? Sine of 90 is 1, isn't it? Now we have the instantaneous power of an inductor is going up and down, up and down, up and down, twice as fast in frequency as the voltage or current by themselves. So if we looked at the instantaneous power of this, we have 1/2 Vm Im cosine 90 degrees plus 1/2 Vm Im cosine 90 degrees cosine 2 omega t minus 1/2 Vm Im sine of 90 sine of 2 omega t. That our instantaneous power on the inductor, P sub L of t, is minus 1/2 Vm Im sine 2 omega t. Where now our instantaneous power is twice the frequency of either the current or the voltage, or the current and voltage, and P sub L of t in the inductor is actually oscillating, or it oscillates, the instantaneous power. And as I tried to describe before, when P sub L of t is positive, then we are actually putting energy into the magnetic field, or energy is stored in the magnetic field of that inductor. When the instantaneous power is negative, it's getting pushed back into the system. And it's like playing catch with that energy. It takes some, then it gives it back. Takes some and gives it back, and it never gets tired. It just keeps, unlike me, one more and I'm good to go, okay? But P sub L of t now is fluctuating, where the energy stored when it's positive in the magnetic field and when it's negative, the energy is delivered back to the source. Now do you see why the power company is getting frustrated? You're just taking energy and then throwing it back at them. Taking it and giving it back. And they're going, would you just take it? And you're not, are you? You say, give it to me. Okay, back. Give it to me, back. The power company, what? You have current going across those lines, don't you? Current is actually flowing through those lines, and those lines aren't ideal. They have resistance in them. And if you're demanding current, they're going to charge you because they're losing, and they're actually having to beef up their ability to supply that current, because now you're maybe asking for higher voltages to sustain what you're really wanting that power to be used for. So maybe you could care less if you keep track of that reactive power, but the power company definitely wants to. So some of you may go and work for the power company, or maybe you already are. Now you would like to be able to keep track of that reactive power, even though it's not being used usefully on your end or on the power's end. power companies in. But we would like to keep track of this energy, since the current is actually flowing in the lines. Now, we've already used up average power or real power. Now we're going to relate this. This is sort of in the opposite direction. This is sort of orthogonal to the real power because it's not doing us any good per se. But all of the machines that maybe we have in our factory are inductive, and so we are, as far as the power company is concerned, you're not only a resistive load, but you have some reactive component. And they want to keep track of both of those. So let's now create or define a new power, and we'll call that reactive power. And we're engineers, so you can't get on to us for being creative with our labeling. Guess what we call reactive power? Q. So we have to mind our P's and Q's in order to keep track of power. We have P in the horizontal direction and Q in the vertical direction. And the way that we will define Q is V RMS I RMS sine, since it's orthogonal to cosine, sine of theta sub V minus theta sub I, and a lot of times we will just call this angle theta, which if we had an interconnection of resistors, L's and C's, that theta would be the net impedance angle because it's the difference between the voltage and current of that mess. And a lot of times we just say, what's the angle in that particular system? We give this another unit to keep track of, and that's VARs, for volt amperes reactive. And we have a way of keeping track of the sine of that angle and the cosine of that angle, and we give those term names also. So now we're going to have a reactive factor, and that's going to be the sine of theta sub V minus theta sub I, and we'll call that RF, not for radio frequency, but this is lowercase r, lowercase f, this is the reactive factor. And if we return to the earlier real power formula, then we have a power factor, which is the cosine of theta sub V minus theta sub I, and that's PF. And we could also, if we go back to our power formula, that was V RMS I RMS cosine theta sub V minus theta sub I. If we solve that for the reactive factor, then that's cosine of theta sub V minus theta sub I, and that's now P over V RMS I RMS. And we actually give this guy a name, the product of our, what? Okay, thank you for your question. Did everyone catch their question? I got carried away. I had my P's and R's mixed up. Power factor is PF. So the power factor is cosine of theta sub v minus theta sub I. And from our average power formula, we can find cosine of theta sub v minus theta sub I, or the power factor, as the ratio of the power that we have divided by V and I. We call that the apparent power. The power company sees that. They say, well, apparently you want this much because you're asking for this much voltage and this much current. But effectively, you're not using all of that because some of your load is reactive. If it was purely resistive, then what's cosine of theta sub v minus theta sub I? Theta sub v minus theta sub I is 0, cosine of 0 is 1, and you are using all of the power that the power company is giving you. So your apparent power is equal to your real power. But when they're not, then this slips a little bit and you're less than 1. That VI is now called the apparent power. And what do we know about if I now had resistors and inductors, no capacitors, interconnected? If I just had resistors and inductors, I would call that circuit an inductive circuit. It really doesn't matter how many R's and L's I have. I just have only R's and L's. That's only going to look inductive. I mean, it has a real piece and a reactive piece, or an imaginary piece, or a complex piece. But now, what do you know about the current and voltage in that inductive circuit? How are they related? If it was purely inductive, how are they related? The current is off the voltage by 90 degrees in a pure inductive. Now maybe I have a mix, but it's still going to be off a little bit, isn't it? It may be between 0 and 90. But what do we know about the current and the voltage? Which one's ahead or behind? If I said the current blank voltage lags. So now we know that in an inductive circuit, the current lags the voltage. You can now tell me something more about theta sub v minus theta sub I. Now, if the current lags the voltage, let's say the voltage angle is 50 and the current angle is behind it, so let's say it's 20. What's the result of 50 minus 20? 30, a positive number. So this now, theta, is positive. And if that angle is positive, if this is how we've defined our reactive power Q, what do we know about the sign of capital Q? If that angle, theta, is positive, what's the sign of a positive angle? Positive. So if we have an inductive load, our Q, the reactive component of our power, is positive. Q is going to be going vertically up. And this corresponds to a lagging power factor. It's not enough to just say, oh, your power factor is 0.95. You have to tell me, is that inductive or, and we'll learn, capacitive? Is your Q positive or is your Q negative? Because the cosine of an angle, positive or negative, is just going to give you a number, isn't it? Positive number. If the angle's between plus and minus 90. Now, let's look at the third case. And this one we should just be able to breeze through. What's the impedance of a capacitor? 1 over j omega c. Or if we multiplied by 1, or j over j, we now have j upstairs and we have j squared downstairs. That's a minus, and I'll just put that minus sign up. I now have minus j 1 over omega c, or this is now minus j x sub c. For a capacitor. Bless you. And now with ice, we know that the current leads the voltage. We now have our Ohm's law in more general terms, in terms of an impedance. What do we know now about the phase of that expression? If we just pulled out the angles from those phasors, and we've labeled the voltage phasor as theta sub v, and we've labeled the current phasor as theta sub I, what's the angle of z sub c? It's now j with a minus sign. So if we went j, then if we revert 180 degrees, that's now minus 90. The angle of that capacitor is now minus 90 degrees. Or theta sub v minus theta sub I is minus 90 degrees. I think you can see what's going to happen. What's P average? That capacitor doesn't absorb any real power, does it? It's an energy storage element if it's an ideal capacitor. Its average power is 0. As we've seen with the inductor, the instantaneous power of the capacitor now oscillates. And when P sub c of t is positive, now with that particular energy storage device, the energy is stored in the in the electric field of that capacitor. And then it just gives it back to the source. It charges up the capacitor, and then it just discharges back to the source. And it just plays catch with that energy if it's an ideal capacitor. The energy is stored in the electric field when the instantaneous power is positive. When it's negative, that energy is delivered back to the source. In a parallel development to what we've just talked about, if I now have only capacitors and resistors in a circuit, I'm going to call that a capacitive circuit. And what can you say about the relationship between the current and the voltage in a circuit that only contains resistors and capacitors? Now at the extreme, just remember ice, right? The current is leading the voltage. And in the extreme case, it's minus 90 degrees. Yes? Yes, so X sub C, the question was, wherever that was, here X sub C, this is the reactance of that impedance. And now if you needed to know more than just the magnitude of that impedance, which is what the reactance gives you, you would need to keep track of the sign, and in this case it's minus J, or minus 90 degrees. So now you only have reactance in reactive power. Reactive power is due to the L's and the C's. And what we will find or learn, I hope, well, let me answer this maybe. Did we say that? Leads voltage. Is that true? If you had a really large plant, factory, and it had a lot of machines in it that were very inductive, you might try to make the power company a little happier by making your plant look less inductive. How are we going to do that? Well, if inductors give you positive Q and capacitors give you minus Q, maybe you try to get rid of some of that positive Q with capacitors. You might have a capacitor bank, and you might flip some of those switches to make your plant look less inductive by putting capacitors in the circuit with your plant. And now you've reduced that reactive power that the power company sees from you. Well, that's a little bit ahead of the game, but that's where we're headed. We want to now be playing with these Qs to make them smaller. Ideally, we want a power factor of 1. We want to see purely resistive loads. It's probably not going to happen. But the power company is going to charge you if your power factor is too low. They're going to say, you are really hurting me because I'm really having to crank things up voltage-wise in order to sustain the current demand that you're asking me to deliver. So let me get off my soapbox. Capacitive circuit is a current leads the voltage in a capacitive circuit. Know about the relationship between theta sub V and theta sub I. If the current leads the voltage, now think of these spinning phasors or these angles. Now the current, in terms of counterclockwise rotation, it has a bigger angle than the voltage. The current leads the voltage. If that's the case, if theta sub I is bigger than theta sub V, what do you know this looks like? This is now negative, isn't it? So when our angle is negative, that corresponds to a leading power factor. Now we're good to go. Now we can say, well, we aren't going to just be playing with pure inductors, pure capacitors, and pure resistors. We are going to have some combination or some mix of all of those. We now have complex impedances. And if we have complex impedances, what does that tell us about our power? We aren't going to just be in the real direction, are we? We are going to have some reactive power, and we will simply call that complex power. Complex impedances lead to complex power. And the expression that we will use, again, we just start going up the alphabet. And since R was already used for resistors, can't use that. But we need a variable for complex power. We've already used P, Q, R. We can't use S. So now we have S is P plus J Q. So S is complex, and I may or may not overbar that. But S in general is a complex number if it has P and Q in it, and those are orthogonal components. This is our complex power. This is our real power. And Q is our reactive power. Excuse me. Now, if we plug in our formulas, what does that look like? S is now V RMS, I RMS. What was P? It was that scaled by the cosine of theta sub V minus theta sub I, wasn't it? And Q, let's say, is plus J, and now let's say that's V RMS, I RMS. How did we define Q? Sine. Now, we can rewrite that using Euler, can't we? This is just A plus JB, and we could, and part of that is the same. V and I are the same in both of those, and now we just have cosine plus J sine. Cosine x plus J sine x. That's just e to the jx. So we can now write this S as V RMS, I RMS, e to the j, theta sub V minus theta sub I. That's our friend Euler. E to the jx is sine x, I'm sorry, cosine x plus j sine x. That's Euler. And that's all we've done to get from bottom to top, for example. Now what can we do? Well, we can separate those complex exponentials and collect the theta sub V with the V and the theta sub I with the I, so that we now have V RMS e to the j theta sub V, I RMS e to the minus j theta sub I. And what are those? Now, that's just the polar form of our voltage, isn't it? Or the phasor form, if we simply write it as V at an angle of theta sub V. Now, how do we get rid of that minus sign? Or how do we account for that minus sign in a complex number? If we wanted to change the sign of the angle, what's the mathematical operation that we can use? Conjugate. So now we need to conjugate I in order to get that minus sign to be there. So that now the S, the complex power, is V RMS as a phasor. That's what I've indicated with the black bracket. And now you just told me that I can multiply that by I RMS complex conjugate. We've now derived the formula that we said we wanted to look at the beginning of the class. And what are the units on this? Here we're getting very creative with units. We've already had watts, vars, volt amperes, VA. That's how we will refer to complex power. This is now just volt amperes. Now, you guys were giving me a hard time about trigonometry, so let's step it back and go even earlier. What preceded trigonometry? Geometry. So now if we look at geometry, can we relate geometry, something visual, to this complex power? Of course, right? So now let's look at the complex power triangle. So what do we have? We have P, Q, and S. P, we said, is in the horizontal direction. Q, let's say it's inductive, is in the vertical direction. Now we can relate that to, or we can sketch a triangle. This is now the complex power S, where this angle theta is theta sub v minus theta sub I. And with Q greater than 0, what kind of a load do we have? Somebody just sketched that complex power triangle and gave it to you and said, tell me, is my load capacitive, real, or inductive? It's inductive because Q is positive. So this is an inductive load just from looking at that sketch of the power triangle. Now that you have this power triangle, you can use your trig. If somebody gave you S, the magnitude, which is the apparent power, and the angle in the form of a power factor, could you derive your real power? Hypotenuse times the cosine of the angle. So now the real power P is going to be the apparent power, or the absolute value, or the length of the complex power, cosine of theta. And I can see that we are out of time, so I will pick up there on Tuesday, but I think you can follow this. It's very visual. I want you to get very comfortable with this power triangle and your P and Q.